In the last podcast, I talked about Ohm's law and power. In today's podcast, I want to talk about equivalent resistance, or how do you, if you have more complicated circuits, how do you make them easier to solve? And so today I'm going to define equivalent resistance for parallel and series resistors. So let's first just understand the basic idea of equivalent resistance. So when we analyze circuits, it's often easier to have a battery and one resistor than say have a battery and 2, 3, or 4 or 100 resistors. And so essentially the goal is to try and make something complicated into something very simple and basic, a battery and a resistor. And so we're going to replace this more complicated circuit by this equivalent resistor, right, to make it easier. But what has to be true is, from the battery's perspective, the current through and the voltage across the equivalent resistor needs to be exactly the same as the combination from which it's replacing. Right, so if we have two resistors and replace it with one, the potential across that new resistor and the current through the resistor has to be the same as the actual situation. So let's look at that and see what that's going to look like. Let's imagine that we have two resistors in series. It's represented by this picture. Here's point A and B on either side of the resistors. So these are in series, and what we mean by series is the current through those resistors are the same. There's just one path through those resistors. And so we can replace those two resistors with one equivalent resistor. Right, and so we want to figure out, well, what's the relationship between those two? But the point is, if I measure the potential between A and B in my real circuit and A and B in my equivalent circuit, it's got to be the same. It has to be the same. And the current, if I measure the current at A on the left situation, it has to be the same as the current in this equivalent situation. So let's apply those rules and figure out how we figure out the equivalent resistance. So we're going to apply the junction rule at, say, point A into point A out of point B. So we're going to treat this whole point as a junction. What essentially that current is equal I1, the current through the resistor 1, is equal to the current through resistor 2, right? They're in series, that current's the same. So I1 equals I2. We thought about this equivalent situation. Well, that current has to be the same. The current through the equivalent resistor is the same as the current through R2, is the same as the current through R1. So I1 equals I2 equals I equivalent. Now let's apply the loop rule, or essentially what that says is the potential difference between A and B has to be the same. Well, the potential difference between A and B is just going to be delta V1 plus delta V2. The potential across resistor 1 plus the potential across resistor 2 is going to be the potential from A to B. In the equivalent situation, the change in potential from A to B is just going to be the change in the equivalent resistor. So we have the change in potential across R1 plus the change in potential across R2 is going to be equal to the change in the potential across the equivalent resistor. So we can apply Ohm's law, right? These are ohmic resistors. We know delta V is equal to IR, so we can substitute delta V1 as I1R1 and so forth. Right, and then we use the junction rule result, right, which we said I1 equals I2 equals I equivalent, so that those are all the same, and we essentially get the rule that R1 plus R2 is equal to R equivalent. So in general, for resistors in series, the equivalent resistance is just R1 plus R2, and if there's more resistors in series, it's just R1 plus R2 plus R3 plus add as many as you need to. Alright, so that's how you add or find the equivalent resistance of resistors in series. Now let's look at resistors in parallel. So imagine we have two resistors in parallel being replaced by an equivalent resistor. Okay, so we have a situation where R1 and R2 are in parallel. What we essentially mean by parallel is they share two ends, only two ends, and there's no other paths. And so we can replace R1 and R2 in parallel with some new equivalent resistor, right? And so we can apply, what we mean by that is the change in potential between C and D has to be the same, and the current into C and out of D has to be the same for our real situation and for our equivalent situation. So we can apply the loop rule. The potential difference between points C and D needs to be the same. And so the potential difference between C and D, in this case we see the potential across R1 is going to be the same as the potential across R2. Is going to be the same as the potential across the equivalent resistor. So we can say delta V1 is equal to delta V2 is equal to delta V equivalent. Okay, so that's fact. Applying the loop rule, now we can apply the junction rule, right, which is essentially saying the current going into C has to be equal to the current coming out of D. Well, the current coming into C, this current is going to split, and we're going to have the current through resistor 1 plus the current through resistor 2. So we have this current is equal to I1 plus I2, which we show right here. Then in the equivalent case, that current, well, all the currents going through the equivalent resistor, and so we just have that current is equal to I equivalent. So we see that I1 plus I2 is equal to I equivalent. We can apply Ohm's law. We know that current is the change in potential divided by the resistance. We can substitute for R1 for R2 for the equivalent resistor. We can use our loop rule result, which said the change in potential across all three of those elements was the same, and we get the following relationship, that 1 over R1 plus 1 over R2 is equal to 1 over R equivalent. And in general, for resistors in parallel, if you have more, that's the basic relationship. 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3, so on and so forth. That ends this podcast.